Lesson 7, I kind of mentioned in 6, goes hand in hand because section 6 was about parent functions and 7 is about transformations. So now it's time to take some of those parent functions that we were working with and to start to talk about what kind of stuff can we do with them to make sure they fit the data that we want it to fit. We'll focus on 3 different things that we can do. The first of which is what we call a shift. Now I'm going to stay color coordinated here today. I'm going to start with some quadratics. And those are going to be in red. Now, the sketches that I do today, you should kind of follow my lead. And I call them sketches. And when I use that term, you should think of a very specific meaning. To me, a sketch of a graph is one that you're going to make without using a table of values. I'm not going to plot specific points because I just want to look at the big picture of what's going on. Okay? So now, and to a certain extent, I wish I just had an X and a Y axis without a grid behind it. Don't pay attention to any scale because you're going to see that, for example, when I plot x squared, I'm just going to say, you know what that is? That's the graph y equals x squared. Now, if you were to find the point 2, 4, you're going to see that point's not going to be on there, right? I didn't draw it to scale. I didn't plot actual points. I'm just talking shape. Because the next thing I want to do is look at x squared plus 2, probably the most basic transformation we have, which results in a vertical shift of up 2. I'm not so concerned about the solution points as I am the effect of that plus 2, that it takes that entire graph and it bumps the whole thing up 2 units. Okay? All the graphs that we're going to sketch today have that same theme. Let's look at kind of the big picture of what's happening to them. Okay? If I jumped over here with the horizontal shift, again, that looks way more like a quartic, actually. But I'm saying, you know what? And you should try to make them as reasonable as you can. That's probably a little bit too wide to be a quadratic, but I'm saying that's x squared. And so now I'm looking right at x minus 2. That is a horizontal shift. And that one's always a little bit tricky because that takes the graph 2 units to the right. Okay, notice it's inside the parentheses, and that does the whole horizontal thing. Okay? Kind of backwards in some ways. Again, if you wanted to make a table of value of x squared and then x minus 2 squared, you would see that's what happens. Okay? That's just kind of how it works out. Make sure you've got these because I am going to get rid of them. And I'm going to switch over to the cubics that I have. Let's get rid of all those. So now I'm talking about my parent functions being a cubic. We've talked briefly about these. The cubic looks something like that. It's got that type of shape. Again, that's x cubed. And minus 1, I just take that point 0, 0, and then I'm just writing here that the whole graph is shifted down 1 unit. Okay, I can clearly see that it's got that shift. Look at h of x down in the bottom right-hand corner. Is this a scenario that we could see? Certainly. Here's my parent function. There's x cubed. Could we do both shifts at once? The most common scenario that we see, actually, is that there's usually multiple transformations going on at the same time. This one is 2 units to the left and 1 unit up. And so now I know my cubic needs to go through that point. And again, that's x plus 2. There's the shift of 2 units to the left, plus 1. there's the shift of up 1. Okay, so certainly you could see that scenario of both happening at the same time. So shifting, that moves graphs. Reflecting graphs, okay? It really is all about the presence of a negative sign, okay? If the negative sign is just simply out in front of the function, and now I'm back with quadratics here. So now I'm back to red. There's x squared. If it's simply just out front, that's going to be a reflection over the x-axis. I like starting with that one because that's probably the most familiar reflection that you've seen. Quadratics get reflected all the time because we work with many problems that are modeled with a quadratic that opens down, right? And putting that negative sign in front of the x squared, that's what it does, is that you now have a quadratic that opens down, okay? Notice on this square root graph, I'm going to use blue today for a square root graph. I'm considering it a function, so remember there's the possibility of those negative answers that we could get. I'm ignoring those, which sometimes with square root graphs we do. Okay, with that negative on the inside, that now has the effect that you're looking at a reflection over the y-axis. So here would be the square root of x. Here would be the square root of negative x. If I wanted to have done a reflection over the y-axis with my quadratic, I would have needed parentheses to put that negative sign inside the square operation. Okay? Think of it along those terms. If the negative is just out front, you're talking about a reflection over the x-axis. Okay? If it is on the inside, then you're talking about that reflection over the y-axis. Okay, I'm going to get rid of those because I don't want them there, because that is not what was going on that graph. Bottom line, if you see a negative sign somewhere in the function that you're working with, really, really good chance, especially if it's out front. You've got some kind of reflection going on, okay? Which you then need to think really closely about, and that's why we split this up into two different situations here. Which type of reflection, over the x-axis or is it over the y? Now, shifts and reflections, okay, they don't deal with shape. So they have some limitations, okay? We can flip the graph either way, over a horizontal axis, over a vertical, and we can shift it left and right and up and down. So, but all we're doing is taking the same graph and we're just moving it, okay? What if we want to mess around and change the shape? Okay, that's where we get into stretches. Back to black, there's a cubic, okay, x cubed. All right, right here, that's what I call a value of a, and notice that it is greater than 1, okay? The term I find that students love to associate with this, and I don't mind it because it actually gives a great description of what's happening on your graph, is they love to say that the graph gets skinnier, okay? It gets skinnier. That 8 is going to cause this cubic to increase 8 times faster. And if you wanted to look at tables of values, you could easily do this with a couple tables in your calculator. And you could compare the two. You could see that as we use the same x value, the y values get bigger a lot faster for 8x cubed. Okay, much, much faster. That's what's going on with the points. On the graph, the end effect is you get this cubic that looks skinnier due to this faster rate of increasing. Okay? Let's jump over to our quadratic. And notice here, we have a value of a that is less than 1. Right? If I made a 1, that's going to give me my parent function. And essentially, there's no change. That's kind of the reference that we're using. Right? That's why I keep coming back to these parent functions, because when I'm saying wider or skinnier, right? Because if you have a value of a that's less than 1, that's the term I find students most often use, is they like to say that that graph is wider. Well, wider than what? Wider than your parent function. That's kind of the one you're using as a reference. You could do the same thing with a table of values here and see that 1/2 x squared is going to increase half as fast. Okay? So as those x values get bigger, this graph increases slower. The same happens with negative x values. The end result is you get this quadratic that looks a lot wider. And again, I don't mind if you use those terms because it gives a good description of what is actually going on your graph. Okay? Shifts, reflections, and stretches. Okay? These give us a lot of options. We can move graphs, we can change their shape. It basically now means that whatever data we have, right, the kind of the starting point is what type of relationship is there. Well, that's going to dictate what kind of function we're going to want to use to model with it. A cubic, a rational, a quadratic, a line. Okay? That's kind of the first step. That's why we started with parent functions, is that splits down all these categories for us. The transformations now allow us to take that particular function and tweak it so that it models the data that we have just right. Now, I mentioned earlier that more often than not, okay, you have multiple transformations going on. Okay, with the graphs that we use in pre-calculus, that's the case the vast majority of the time. We've already seen one. If you go back to that cubic that we did under shifts, we saw one that had 2 shifts. So that kind of had 2 transformations. Okay, the situation here is we have a cubic. So there's x cubed. 3 things going on. And notice how I switched the terms. You should kind of be ready for either. I mean, if you're dealing with a graph like a cubic or a quadratic, you can change the order of the terms. And I would recommend doing that because I find that if you take the equation that's down at the bottom, negative x or 8x cubed plus 2, students tend to find the transformations easier with that one. Whereas the first one, sometimes they get a little confused and aren't totally sure. Okay, 3 things are going on. Number 1, with that negative sign, we have a reflection. It's out front, so it's over the x-axis. We have that 8 that's going to make the graph skinnier, and it's going to get shifted up 2. Okay, so it's going to go through that point 0, 2. So now as I draw it in, notice the tails of my graph are going the other way, and I'm trying to make it, okay, noticeably skinnier, as this would be negative 8x cubed plus 2. No specific solution points, right? I'm just sketching. Okay? I got the reflection with the tails going the other way. I probably could have done a better job on that one of making it skinnier. Okay? It looks a little bit skinnier, but probably not as much as it should. But you can clearly see the shift as well. Let's hop over to this one. Got ourselves another quadratic. There's my parent function. Okay. Great point. If you want to pause with these and kind of, see if you can graph it on your own, it's a good idea. I see 2 transformations. I see the shift up 2, and then the 1/3 makes that graph wider, right? How much wider? A third. That's the number impacting how much wider. But again, on these sketches, they're not to scale. That's not my concern. As we kind of get more familiar with the transformations, we'll be more concerned about going to tables of solution points, and really looking close at how they're changing. Again, right now, this is kind of a big picture look at transformations. All right, two more of them. I'm going to switch over to blue here. I'm back with the square root function. Something like that. Again, ignoring the negative solutions on the bottom half. I see a reflection and I see a horizontal shift. Okay, it's out front, so it's getting reflected over the x-axis, which would be like right there. But then it has to start here and get shifted 2 units. Which direction? Remember, this is the case that can be a little bit tricky. 2 units to the left. And would look something like that. Negative square root of x plus 2. Okay? Last one. Kind of our favorite function of the lesson. The old quadratic. Okay, there's my parent. I can see 3 things going on. I see this 2 out front, which is going to make the graph skinnier. And then I see 2 shifts. I see this minus 4 on the inside that tells me 4 units to the right, and then a minus 3 at the end to go 3 units down. Which means I'm thinking about right there. Okay, so that's where my vertex is going to be. That's the only point I'm actually going to shift. And again, that is 2x minus 4 squared minus 3. Okay, it's got the vertex labeled for the shift over 4 and down 3. And again, I tried to sketch it so that it's noticeably skinnier than the parent function. Okay, because again, that's the effect of that 2.